So now it's time to do problem 1a. Recall that we are trying to derive a differential equation or system of differential equations to compute, or that could be solved to compute, the concentration of B as a function of X. So we specified that we would need a differential control volume between position X plus delta X. So now we should start with a balance on B because that's what the question is asking for. So we use a balance equation. So input minus output plus generation minus consumption equals zero. Equals accumulation. But this is a steady state balance. Let's say somewhere it says steady state. Yes, steady state is stated right here. So things do not depend on time, so let's say that that's zero. So when we say input, we're referring to what goes into the control volume and what goes out of the control volume. So the amount of A coming into the control volume is going to be F times CA. And you could balance the rate. I'm sorry, we're not doing a balance on A, are we? I should have written what we're doing a balance on, B. So the amount that comes into the control volume is FCB. We could say delta T implying the amount that comes in during some time increment delta T, or we could leave the delta T off and talk about the rate at which B comes in. So I'll keep the delta T there. A common mistake is to say, well, there's no B going into the reactor, therefore there's no B going in. But remember that our control volume is going to occur at an arbitrary position of X. So if X is somewhere in the middle of the reactor, then during the volume that comes before that portion of the reactor, there was some B created. So there would be B input into the control volume. So now that's our input. It occurs at X. Our output is going to be FCB delta T at X plus delta X. The generation of B is going to be K2 A star times the volume of the control volume. So plus K2 CA star times AC delta X. That's the volume, cross-sectional area, times delta X of the control volume. Now B is not consumed in this reaction because there's no reverse reaction here. That does not exist. And so this is our balance equals zero. To turn this into a differential equation, we have to generate the definition of the derivative. So what we're going to do is divide through by F. We're going to move this stuff to the other side of the equation. So I'll change that to the left-hand side. So I'll say CB at X plus delta X. Oh, by the way, this would also be a rate. So to get a total amount, I would need a delta T, and the delta T's can actually cancel. So if I say CB at X plus delta X minus CB at X divided by delta X, that's going to equal K2CA star times AC divided by F. If I take the limit as delta X goes to 0, this is going to become dCB dx. So this is our first differential equation. dCB dx equals K2AC over F CA star. Okay, I'm going to put a box around it, and I'm going to label it equation 1. Notice that this equation, or CB, is going to depend on CA star, and therefore this equation would not be sufficient for calculating CB as a function of x. So we need to do a balance on CA star. So let's look at that. So we're going to do it as input minus output. So F CA star delta T evaluated x minus F CA star delta T at x plus delta x. Now the generation of CA or star would be K1CA. Then there's consumption minus K negative 1 CA star minus K2CB times AC delta X delta T equals 0. So what this is going to translate to, I do the same thing that I did here. I define the definition of a derivative in terms of CA star, and this should become dCA star dx equals AC over F times K1CA minus K negative 1 CA star minus K2 CA star. And I'm going to box this and call this equation 2. But notice that this includes a CA in it. So now I have two equations. They describe the behavior of CB and CA star, but I've introduced another variable. So now, in order to get a third variable, I'm just going to look at this kinetic equation. If I do the same procedure, I should get dCA dx equals AC over F times K negative 1 CA star, that generates CA, minus K1 CA. That's my third equation. And so I have three unknowns, CB, CA star, CA. You could call them dependent variables. They depend on x. So I should be able to solve the differential equation assuming I know the boundary conditions. Remember that we're asked for the boundary conditions. So in this case, I know my concentrations at x equals 0. So let me just write the BCs. So CA at x equals 0 equals CA in. CB at x equals 0 is 0. CA star at x equals 0 is also 0. So I'll box these because they're being requested, and that should be the sufficient answer to the question.